All right, inverse functions, or inverse of a function. First of all, if f of x, g of x are said to be inverse functions, or one is the inverse of the other, several things will occur. And one thing that we know will occur is if I take f of x and plug g of x into it, the output will be x. Or if I go backwards and take g of x and plug f of x into it, the output will also be x. So basically that means that the inverses of each other. Now the way we can say inverse, the symbol for inverse, is f to the negative 1 or g to the negative 1, or anything where you say negative 1 means it's the inverse of the other. And this actually reads g inverse. That actually reads f inverse. Actually, the mathematical sentence for it is. All right, so let's look at some more inverses. Well, you know what? Before I go any further, understand this. That's one way we can show inverse. That if f of g of x equals to x, and also g of f of x equals to x. So prime example is this. Suppose I gave you f of x equals to x squared, and g of x equals to the square root of x. So if I found f of g of x, I basically take g of x and stick it into f. So the x is now the square root of x squared, where the square root of x squared is x. So that means f of g of x equals x. So that part checks out. And then if I check g of f of x, I would take g of x, which was the square root of x, and replace that x with what f of x is. F of x is x squared, so then I'll put x squared there. So the square root of x squared is definitely x. So g of f of x is also x. So that's two different ways that we can actually show, well, that's one way we can show inverse. I can take one and place it to the other. Another way I can show inverse is this. If I looked at the two functions, for f of x and g of x, and I actually interchange domain and range, we can show the inverses of each other. So what I mean is this. If I told you that f of x, has the ordered pairs, so x and y, 2, 4, let's think about it, and things that it was x squared. So 2, 4, 3, 9, 4, 16, and so forth. If I want to find the inverse of it, inverse of f of x, the domain and range would switch places. So what was the domain, the x values, would become y values, 2, 4, and 3. And the corresponding y values would become x values, 4, 9, and 16. So whatever happens, that's guaranteed the inverses of each other. So you have an ordered pair that was 2, 4. In the inverse, the ordered pair would be 4, 2. So that's one way you can find inverses. The domain and range change values. So wherever they were, they switch places. A third way you can actually find inverses is this. If you actually thought about the graphs for both of those functions, they're basically going to be a mirror image about the line y equals x. So it's kind of like we talked about one-to-one functions and even and odd functions and so forth before. We talked about having that line that's symmetric about the origin and so forth. But in this case, it's not symmetric about the origin, but do have to be symmetric about the line y equals x. So a prime example of the function x squared, I would look at it as this, 1 to 1. So x is 1, y is 1. X is 2, y is 4. So this is 1, that's 2, this is 3, this is 4. So here's another point. So the graph looks something like this. So that'd be the line to the y equals x squared. If I graph y equals square root of x, That's actually tomorrow's night's video or whatever. But if I graph that right now, it'll look like this. So at 0, the output's 0. At 1, the output's 1. Does something like this. So if you thought about the line y equals x, it would be this line. So theoretically, if you folded that down that line, down this crease here, you should see a mirror image on both sides. My rough sketch may not be convincing enough, so let's look at it with the actual graph. So let's graph the first one, which was x squared. So I'm typing x squared. That's its graph. And the second graph would be the square root of x. And here's its graph. And then the next thing on the graph is the line y equals x, y equals x. So I'll graph it. I get that line. And if you can visualize taking this piece of paper, folding it down this blue line here, and you should see that the lines lie on top of each other because they're a mirror image about each other. So I folded it down this blue line. I tried to square my window up a little bit. But if I folded it down this blue line, I changed it a little bit so I made my window more square so it looks more equal on each side. But if you fold it down this blue line, you should see that this red line and that green line should end up lying on top of each other all the way down. So in between there. Now, you don't really have a domain for the other function, the square root function after 0, because in the other function, square root of x, it can't be smaller than 0, so all the negative numbers don't exist for it. But on the right side of the y-axis, you should see that both lines lie on top of each other. So it's a third way you can prove two functions are inverses of each other, if they are symmetrical about the line y equals x. So functions are inverses if they are symmetric about the line y equals x. So you had a graph for it. You just visualize that graph, y equals x, which is x is 1, y is 1, x is 2, y is 2, x is negative 1, y is negative 1, and so forth. And you actually see if they actually are symmetric, mirror images about that. If they're not inverses. All right, so new example. So let's find the inverse of this function. Go pause it. Actually really easy, but go ahead pause it first. Let's go find the inverse of it. So pause the video, write down this example. I want to explain how to find the inverse. So if you're given y equals 3 times x squared plus 2, inverse, you simply interchange x and y's. So where y was, you're going to make it x. Where x was, you're going to make it y. And afterwards, you like to solve equations for y, so we should take that equation and solve it for y. So if I had that equation and I solve that for y, you probably subtract 2. And you get x subtract 2 equals a 3y squared. And then if you solve that, you probably divide by 3. Give you x subtract 2 over 3 equals a y squared. And to solve that equation, you square root both sides. So the square root of x subtract 2 all over 3 equals the inverse. So I can know its inverse and put y to the negative 1. That way I know it's not the same thing as the original y. So this is it. They should be inverses. So let's go a graph though, just to make sure. So this is the first equation and this is the inverse equation. I'm going to take it back to my graphing calculator and see if I can recognize whether or not they are symmetric about the line y equals x. All right, so here's the first equation, 3x squared plus 2. If I graph it, there it is. And there are the other two. The one in green is the inverse function, and the one in blue is the y equals x function. So here it is, the line that they should be a mirror image by, or symmetric by. And if you can kind of visualize me folding this thing over so that we're both, down a crease down this line, you should see that this green line winds up coming over here and will lie on top of this side. If you can visualize that, this green piece will fold over and it should be over there. Or better yet, if I take a better look at that, yeah, this green piece actually matches with this side here. If you actually fold them together, you should see this piece comes up and folds, and it should lie right on top of it. Basically, what you ought to see is this square root function is like half of a parabola. If you had the opposite half, or the negative half, it would come down here, and it'd be identical to this parabola turned sideways down there. But yeah, they're definitely inverse of each other. They're definitely symmetric about the line y equals x. All right, so last few things though. You may remember, in order for a graph to be a function, it's got to pass the vertical line test. Basically means if I drop a vertical line on this graph, and as long as it touches in one place, it's fine. If I touch it in two places, it would not be a function anymore. So this graph passed the vertical line test. Because if I drop the vertical line on it, it only touches it once. There's a new test called the horizontal line test. Horizontal line test. Basically, all it tells you whether or not your inverse will be a function or not. So if your graph actually passes the horizontal line test, your inverse should be a function. If a graph does not pass the horizontal line test, the inverse should not be a function. So in this case, the inverse of this function should be this. But technically, when we take a square root of a number, we should say plus or minus. So our answer for this should be a positive or a negative square root of x subtract 2 divided by 3. So the other half of that curve should be this piece. Make it into full parabola. And if we look at that, that wouldn't be a function. Why would it not be a function? It wouldn't pass the vertical line test. Vertical line would strike it twice, meaning it's not a function anymore. But you could test that before you even flip it or whatever by looking at the original graph. If the original graph doesn't passes the horizontal line test, then its inverse is a function. If it doesn't, the inverse is just not a function. We can still graph it, we just know that it has to have an upper half and lower half to the curve. Let's go make this a good note as well. Horizontal line test, then is inverse is a function. It should have said if it passes the horizontal line test. So if it passes the horizontal line test, that means that the horizontal line does not strike it twice. This one, it struck it twice, so it didn't pass it anywhere. But if it passes the horizontal line test, then its inverse is a function. You can make that look better than I did. I think that's all I have to tell you about inverses. That being said, you can turn off the video, and good luck with tonight's homework.